A model can leak prompt text quietly. Here's a fast detector. You'll see how to connect the pieces into a workflow that plants canary strings, scans outputs, and raises leak alerts. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Prompt leakage is subtle. A model can answer normally, while secretly echoing internal instructions. That creates a blind spot for operators. Canary token detection gives you a known, harmless marker to plant where only the server knows it. When that marker shows up in assistant text, you have a deterministic signal someone dropped internal content. The idea is simple. Put a unique string into the internal system prompt. Then watch assistant responses for that string. A match is cheap to detect and very high signal because only your server should have placed that exact string. This won't stop sophisticated data exfiltration, but it turns silent leakage into an actionable incident that you can triage. We will build a minimal pipeline that plants a canary, checks responses, groups hits by route for triage, redacts logs, and produces an alert. That flow maps directly to common server architectures and helps you catch mistakes before real secrets leave your stack. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we plant a canary inside the internal prompt so there is something to detect. This snippet creates a harmless canary and embeds it into system prompt. It derives the canary from app metadata, so the marker is tied to a specific environment, then concatenates it with the internal prompt text that the model will see. Before any model call would happen, the code checks token in prompt to confirm the marker is present. The important moves are generation, insertion, and verification, so you prove the detector has a known marker to watch. In production, you would generate a unique value per environment, prompt version, or tenant, so one hit points to a smaller blast radius. The output shows the token and confirms it was embedded, which proves the detector has a known marker to watch. Detecting a single response is the next step to confirm leakage. This example scans one assistant response for the canary string. It treats model output as the raw assistant text and performs an exact substring check for canary. That Boolean maps directly to an action decision, so the first detector is fast and cheap. The code shows how to turn a match into an immediate flag and how to keep non-matches quiet. This exact match approach avoids fuzzy false positives at the start and makes alerts easy to reason about. The output reports whether a leak was detected and which action the application would take, letting you test the end-to-end detection logic without complex parsing. Once you can spot leaks, you need to know where they come from so you can prioritize fixes. This code ranks leaked outputs by route, so the first investigation target is obvious. It stores pairs of route and assistant text as events, filters events containing the canary, and then uses counter to aggregate hits by route. The most common call returns the route with the largest observed leak count, which helps direct your triage to the API endpoint or prompt version causing most incidents. By counting occurrences, you turn scattered hits into a clear pattern. The output shows the top route and its leaked output count, which gives a practical starting point for debugging. Redaction stops the detector from creating a second leak when you persist logs. This snippet redacts the canary before a detected output is written to logs. It builds a log line from the assistant text and then replaces canary with a neutral label, so the raw marker does not propagate into long-term observability systems. The code then verifies kept token is false after redaction to ensure the sensitive string was removed. That way you can still count and alert on the incident without copying the proving evidence into dashboards or tickets. The output shows whether the log still contains the token and the final safe line length, which confirms the redaction step worked. Finally, we wrap detection into a tiny operational path that produces safe alerts for operators. This example turns detection into a tiny incident path with a scanner and alert list. The scan output function performs the two required moves. It records whether canary appears, and it produces a redacted safe field for downstream handling. When a leak is found, the branch appends one alert with service and type only, keeping the marker out of operator notices. This keeps healthy outputs quiet and surfaces only meaningful incidents. The output shows the incident status and alert count, confirming the leak became a detectable operational event. In a production mapping, you would wire that alert list into your paging or ticketing system and store redacted evidence in safe buckets for post-mortem. What this is: a planted marker and a lightweight detector that turns silent prompt leakage into an operational event. When to use it on any server-side prompt pipeline where you control system prompt and want early detection of accidental exposure. One thing to watch: canaries are a detection tool, not a prevention control, and they must be rotated and scoped so a single marker hit does not explode your blast radius. Try one focused improvement next. Rotate a unique canary per tenant and per prompt version, and sample responses by route, so you quickly see which prompt versions leak while limiting noise. This targeted rotation and sampling will make alerts precise and investigations smaller. If practical AI engineering helps you, subscribe and watch the AI engineering videos.